a little bit the seats here. So good morning to you all. Thank you again for coming back. Fourth day now. God, this is indeed quite a bit of a marathon here, especially for you. I was yesterday a little bit slower in the program than I according to schedule, but I think it's okay because we can make up some things I want to cover. Actually, tomorrow we can do this a little shorter. But I would like to go back just very briefly to this idea which we discussed yesterday. And this is this idea that if you coordinate a substrate to your catalyst, if that gets irradiated and if it's doing a homolysis, this can be a starting point for the for a radical reaction. And I think the chemistry which I showed you in the end was that we can apply this principle to nitroalkanes, especially to these nitroesters, which are very easily deprotonated, forming an anion. And then this anion, I think I had it even on a previous slide here. These anions can, once you make the anion such a copper-2 complex, can then be very easily oxidized, and again it might be just a homolysis of that copper-oxygen bond, which makes copper-1, and then the radical, and we use this for a starting point. And the other thing which we discussed was that these type of homolysis reactions can be very fast, and I would like to go back to this idea as well and just show you a few more examples for this. But before we start, how about you guys? Did you ever run photoreactions? So let me know. You see here it's still the same number from yesterday because it's still the same presentation. So how is it for you? Did you do something in this regard? With some of you I talked during the tea breaks, and they told me a little bit what they were doing. How is it with you in general? Okay. Okay. Not relevant for my project. You never know. But that's okay. And it should be clearly seen that photocatalysis is not solving all the problems you might have in a synthetic project, but it's a very good technique to have around. And the same will also be true. I would like to discuss with you in the second part today, I would like to discuss with you some electrocatalysis reaction. And it's the same thing. It's good to have it around. And nowadays it makes it relatively easy because you can have these kits which you can very easily store, but then also build up an electrochemical reaction and get started on this. Okay, so it looks like it's about mix. Some of you have done it, some of you have not done it, but maybe you will do it at some point, and that is absolutely fine. Let me tell you one thing which we did and which relates again to this idea that these homolysis reactions are very fast. And so we were wondering if these homolysis reactions are that fast, then maybe we can use not just copper, maybe we can use iron. And we did something very simple here. We used iron 3 chloride as a means to make, oh wait a minute, where do we have the pen somewhere? Excuse me. Ah. Oh, great. Thank you. Thank you. Okay. So we started asking a very simple question. Can we take iron 3 chloride, I draw it down here. Let me see if it lets me do it. And if this gets irradiated, and you can see we have to do this because we don't have a ligand here. We have to do this in the at lower wavelengths. But again, the LEDs for 365 are around. And so we were simply asking the very simple question, if we do this, can we generate chlorine radicals out of this? And this would involve a reduction of the iron 3 to the iron 2. And we were interested in doing this for the one reason that obviously iron catalysis might be very promising if you do this. And if you think about this, so far I would say there are not so many reactions around you can really catalyze with iron. A lot of the reactions you mediate with iron. Best known is the reduction of nitrobenzene to aniline. That has been done on a technical scale with iron or iron 3 chloride in order to make from with iron. Not with iron 3 chloride. It's done with iron in order to make from nitrobenzene to make aniline, right? But there are not so many reactions which are really catalytic. And so we were wondering if this is helping, or this could be a starting point for us here. And you can see what we are ultimately doing. We have been done a hydrogen abstraction from aldehydes, and we are utilizing, and again you can look this up in the bond dissociation tables. We were utilizing that the carbon-hydrogen bond on an aldehyde is weaker than the carbon-hydrogen bonds like in an alkyl chain or so. So that gave us a very good indication that we should be able to do this selectively. But the other thing which we also were hoping to achieve or consider, and this is why we choose aldehydes, is iron 3 chloride might not only be a source for a chlorine radical, but iron 3 chloride is a pretty good Lewis acid. And we all know that Lewis acids can coordinate with carbonyl compounds. And we were wondering what this would, if that would have a beneficial effect on the activation of these aldehydes. And indeed, it does. We had some calculations. We had some collaborations with a group in Chile. And they did calculations, and they calculated various complexes of the aldehyde with the iron 3 chlorides. It's something you can see here, maybe not too clearly. And they indeed calculated that the bond dissociation energy of that carbon-hydrogen bond should be lowered, and quite a bit lowered, by about almost 7 kcal per mole through the interaction with the iron Lewis acid. And that also helped us probably to understand is that when we used for the same chemistry copper 2 chloride, we talked about this yesterday, this was the initial observation by Kochi that you can generate the same chlorine radicals also from copper 2 chloride, but we saw that this works with much lower yields, so the iron process was more effective. And so we were doing this, and then again you see here we are generating iron 2, and this is why I would like, and maybe I had a tutorial question for this, but maybe we can do this now and come back to this nevertheless a little bit later in a slightly different context. So when we make these acyl radicals, then by the hydrogen abstraction, in the same process we are making from iron 3, we are making iron 2. And so we had to think about what we can do in order to bring then eventually in this process to bring this back to iron 3. And so that was the reason, in principle, this could, we go through the mechanism in a moment, in principle, this could according to the reaction mechanism, happen by itself. But we found out that if you add an organic co-catalyst, and this is what we did here with this diphenylanthracene, that this reoxidation path, this reoxidation is much more effective. And so this is why you see here that we're using a combination of two compounds, the iron 3 chloride and the diphenylanthracene. And we would propose that we also go through two photocatalytic cycles. And let me show you this. And so what we think is we have an iron photocatalytic cycle and we have a photocatalytic cycle which comes from this anthracene molecule. And so in the iron photocatalytic cycle, what should happen is that we excite the iron 3 chloride. And again, we had a chloride source in there, so we had probably an equilibrium of FeCl3 and FeCl4 minus. And then once this is excited, it can dissociate a chlorine radical, and then at that point it becomes iron 2. And so now the chlorine radical can do the abstraction from the acyl radical. This acyl radical, and again this will become a little bit more important in a moment because I will show you a second way to make such acyl radicals. This acyl radical is nucleophilic. This is always known. The radical is not, there's no electron withdrawing capacity from the carbonyl group because it's orthogonal. The pi orbitals of the CO bond are orthogonal to the radical center. And essentially the phenyl group, and it works like a donor. So it's known these radicals are nucleophilic, and therefore they should react with electrophilic alkenes, and this is indeed what they are doing. And so once we do the addition, then we go and have this radical here. And then this radical, in order to close the catalytic cycle, if this radical gets reduced, let me do this here. So if this gets another electron, we would go through this carb anion, and if this picks up a proton, then you get this compound. And in principle, this electron, it could come from the iron 2 chloride. If the iron 2 chloride gets oxidized, it would give away one electron and would go back to the iron 3 chloride. But we found that this is not so effective. And therefore, we found that it is more effective to have an electron, an organo photocatalyst in there, which might do this mediation more effectively. And that is that's why we are using this diphenylanthracene, because when you excite the diphenylanthracene is very easily able to oxidize the iron 2 to the iron 3 back, and then you're forming such a radical anion here, right? This molecule from the excited state takes one electron from the iron 2, makes such a radical anion, and this radical anion is a very strong reductant, and this is ultimately reducing the radical, makes this anion, which then gets protonated and finishes the reaction. And so this is a classical Giese reaction that is the name or Giese reaction comes from the person who has invented this, not photochemically, but Professor Giese from Germany, and then later on he was in Switzerland. He developed a lot of radical chemistry in the thermal way, and especially such reactions where you add radicals to alpha-beta unsaturated alkenes, and this way these type of reactions became known as the Giese reaction. And so this was one way how we could make iron work catalytically. And then we used actually the same type of principle with just a different precursor. Not just with an aldehyde, we also used such trioxanes. And these trioxanes, it's the pretty much same idea that first of all, they're quite easily to come by because it's essentially the trimerization of an aldehyde. And that can occur under acidic conditions. And in fact, the trioxane for R equals hydrogen, that is commercial. And this is actually an equivalent to formaldehyde, right? So we could have used formaldehyde, but to use this trioxane is actually even more convenient. It's formaldehyde is a gas, or you have it in an aqueous solution, but the trioxane is a pretty good alternative if you want to use formaldehyde. And so what this does here is, again, it has a hydrogen atom which is privileged to be deprotonated, because you see, once you do this, not deprotonated, that's the wrong term, need to be precise here, so where the hydrogen abstraction could be occur. That's what I should have said. Because if this happens, we have seen yesterday that radicals which have in the neighbor position have an heteroatom like an oxygen are especially stable. And so this radical has even two oxygens next to it. So we felt that this should work. And now we did the same type of chemistry. Again, we used iron 3 chloride. And in this case, we're again using an anthracene. I don't really know. We tried this, and my co-workers were assuring me that in this case, the dicyanoanthracene worked better for them. And you see in the previous example, they used diphenylanthracene. From the potential tensor, it should have been similar. I was not sure if it is, you see, this was the publication came out 2 years later, and it's two different co-workers. So sometimes it's also co-worker dependent, right? Which type of system they like. But it's very similar. So the reaction conditions are very similar. And again, the radical you're generating here is again nucleophilic. And so consequently, it will react with electron deficient alkenes. And so that is one of the things where the limitation is with this reaction, but also with the direct activation to the alkenes, we have not been able to add this to even styrenes, which usually are good acceptors, right? But it was only working with electron deficient alkenes. And I would like to tell you about that problem a little later as well. But the polarity always has to match. And even with styrenes, these nucleophilic radicals, it seems not to match any longer. And I nevertheless will tell you that there might be ways to go around this. And so then in this case, if we are again able to get these type of adducts here, you can isolate them, but you don't have to. And then if you heat this up a little bit, so we're doing this at room temperature, but if you heat this up, for example, in a microwave, then in the first step, the iron is the photocatalyst, the iron 3, but then you can also utilize the properties of iron 3 as a Lewis acid. And you can see here you have an acetal, and acetals are deprotected to the carbon groups by Lewis acids or by Bronsted acids. And so you can see if we are doing this, we have overall added a formal group to our alkene, right? So we have added essentially hydrogen and an aldehyde to these two centers. And clearly, and I'm not pretending that this can rival in any way the industrially used process of a hydroformylation, which is very broad and is being done on million-ton scale. But nevertheless, it is a formal hydroformylation which is iron catalyzed. And let me just remind you. All right. Let me just remind you of the hydroformylation. Here. Right. The hydroformylation is one of these reactions which is really fantastic in terms of atom economy, making no waste. And so the hydroformylation was this reaction where you add across the double bond, where you add hydrogen and carbon monoxide, and you need a catalyst for this. The catalyst can be either a rhodium-1 catalyst or a cobalt-0 catalyst, and then your product, typically, with a few exceptions, are the hydroformylated product where the aldehyde group is on the terminal end. And as you can see, this is, I think, in the beginning when this chemistry was developed, this was in the 1930s, there they used cobalt as a catalyst, and later on they found out that rhodium is much more effective, but of course also much more expensive. And so I think these days, depending on the company, they use both types of catalysts, and they, and again, this is done really on tremendous scale, so our process clearly cannot compete with this, but nevertheless, we do a hydroformylation of electron deficient alkenes, iron catalyzed. Just let me remind you or ask you about this reaction. I'm not sure how familiar you are. So typically, you get this onto the terminal position, and this is true when this is an alkyl group. Are you familiar with that reaction? Do you know also what substrates will give you the aldehyde group on this position? Have you learned about this in any of your other reaction or lectures? Because it's useful to know. So usually it wants to go terminal, because whenever you have, like, for example, you have like a rhodium carbonyl hydrogen complex which might have ligands on here. If this adds to the double bond, for steric reason, it wants to add, it wants to do something like this, right? It wants to add the hydrogen to the smaller substitute, to the smaller side, and then the big rhodium fragment with its ligands around this, it wants to add it to the terminal side. So that's steric reasons. And then if it is doing the reductive elimination, it will go through such a rhodium acyl complex where it has where the carbon monoxide has been inserted, and then it will get hydrolyzed and form the aldehydes here. The situation changes. This is the one, I think, the one class of alkenes you should remember. There are a few more which give the branched products, but especially styrenes give you the branched product. And the reason for this, so let me just point out what it gives you. So here the hydrogen adds to the terminal position, and the aldehyde goes to the internal position. And the reason for this is that the arene substituent So if I have my alkene here, let me see that I draw this well. The reason is that your catalyst can also coordinate with can also get an additional coordination to the phenyl group. And then this way, the addition of the rhodium fragment will be directed to the, it will be directed to the internal position, right? So it coordinates with the phenyl ring, hydrogen adds, and then the rhodium is adding here. And so this is the one exception you might want to remember. And this is, of course, also quite interesting. This gives you the opportunity, and this has been done. If you have chiral ligands, this gives you an opportunity to develop asymmetric hydroformylation, chemistry. And so, and these type of compounds are, of course, quite interesting, because if you convert the aldehyde group to the, if you convert the aldehyde group to the carboxylic acid by an oxidation, and if you're not using the simple styrene, if you're using all right. Yeah, wait a minute, I have one carbon too many here. So if you start with the I put this wrong. It should be here. It should be like it is here. I'm not sure how I can erase with this this compound with this pen here. Do you know which compound this is? Have you ever taken it? This one, the product. That's ibuprofen. So if you have a headache, it's something you might do. And I don't think it's synthesized by hydroformylation chemistry. It's done in a different way, but hydroformylation would be a possibility. And then I don't know if you, I'm not sure how this is here in India. If you buy what you buy, do you buy ibuprofen, just ibuprofen as a racemate, or do you buy the enantiomerically pure compound? Because the enantiomerically pure compound is, in the S enantiomer, is more effective. It's an interesting story. The R enantiomers actually makes a headache, and the S enantiomer relieves you from the headache. So if you take the racemate, but the S enantiomer is about 20 times more effective to kill the headache than the R enantiomer, which will give you the headache. And in addition, our body is transforming the R enantiomer into the S enantiomer. Don't ask me why, because evolution probably didn't know about ibuprofen, but it definitely works this way. And this is one interesting strategy from pharmaceutical industry these days. The ibuprofen patent was long gone, but since the realization these days is that we should not market racemates any longer as drugs, that you always have an advantage if you take an enantiomerically pure compound, simply for the fact that then you only have one compound in your body, and if you have two compounds in the body, then the other compound might have undesired side effects which you don't want to have. And there have been some very dramatic examples in the literature. If you ever want to read up on thalidomide, for example, that's the classical example where one enantiomer had a pain-relieving effect, and the other one would cause burst effects if you would have taken it during pregnancy. And so then these days, if you now market the S, the enantiomerically pure compound, you can get a new patent, or you can get new patent extension. That is what is called, if you read it up in the literature, this is called the chiral switch, meaning you switch from racemic pharmaceuticals which are in the market to a non-numerically pure one, and then you can apply again for an extension. You will not get the full patent. You will not get another 20 years or so. You get less, but it's an incentive from the governments to make this more interesting. And so check the next time you're in a pharmacy, you probably can buy both. The one is called just ibuprofen, and the other one is called S-ibuprofen. And the S stands for the chiral center, for the S configuration. And of course, it's more expensive, right? As you probably can imagine, right? So again, so we've been able to do this this type of hydroformylation. Let me see where it was. So it was here, and then what we liked about this is that we can also install the carboxyl groups right away, because if we heat it up under oxygen, we will oxidize the aldehyde automatically. And if you use a substituted trioxane, for example, the methyl variant here, you can also do a hydroacylation. And so again, as I said, this is a small contribution to carbonylation chemistry, which cannot compete with the industrial used hydroformylation processes, but nevertheless, I think it's a good step to show what iron can maybe do. And so here are some of the examples which you will have in the handouts, and then we actually could do both processes together. So we could first do a hydroformylation, generate an aldehyde by using the trioxane. So we showed this on the vinyl sulfane, on the vinyl sulfone here, and you can see we're doing this reaction, the photoreaction with iron. Then we deprotecting with iron to generate the aldehyde. And then we utilize this first chemistry I showed you, that we can now in a second photoreaction activate the aldehyde and react it with a second alkene in order to get these two compounds, two alkenes stitched together through a carbonyl group. And everything is iron, right? So we do the two photochemical steps with iron, and we do the deprotection with iron. And again, I think that is something which might point to the fact that iron can actually also be an interesting metal for catalysis. So again, nucleophilic radical, these acyl radicals, these radicals we get from the trioxane, will react to electron deficient alkenes. And of course we tried at least styrene, and you know, then you get always, my coworkers always got this good advice from me as a advisor, and they said, try an electron deficient styrene, right? To do the styrene which has some electron deficient groups. Didn't work. We couldn't really do it. It was for maybe even various reasons why that would not work, but we were unsuccessful. But then, and that's the last story I want to tell you about this copper and iron chemistry. Again, new co-workers, and they said, maybe we do it again with copper, and maybe we generate the acyl radicals not by a hydrogen abstraction, maybe we generate it from an acid chloride. And so again, this is the one issue I would like to point out, that new slide here. Come on, let me do it. Okay. That you can generate the same type of radicals by different photocatalytic processes, right? And so the first one I showed you is that we would use the aldehyde, generate a chlorine atom, utilize that the bond dissociation energy is the weakest in this aldehyde, and then by abstracting the hydrogen, from the acyl radical. But The alternative to this is that you could start with an acid chloride and then do with the copper-1 photocatalyst. That is something we have seen yesterday quite a bit, to do a reduction. So copper-1 goes to copper-2, and you are forming the acyl radical, and in this case you're extruding chloride. So both times it's the same radical, but in the second case we would be able to take just about any R group here, and we would be able to add the acyl radical to the alkene, and suddenly everything worked. Styrenes worked, unactivated alkenes worked. Didn't really matter. And one of the reasons we believe, again, which helps us here, is that we have this synergistic action from the copper-2, right? We are generating from copper-1 to copper-2, and so you can think about that we are generating some kind of a copper chloride, and this copper chloride complex, which still had ligand on there, so we were using I show you about this, I talk about this ligand in just a moment, but this is probably very rapidly, maybe even simultaneously, interacting with the radical, entraps it and stabilizes it. And then by a reductive elimination, you see we are getting a different product, of course, now. So now we are getting the product which had the chlorine molecule in there, and in the reaction before we had the hydrogen in there. But again, as I say, this worked with any alkene suddenly, and we believe it is because we have an interaction either in this way, that the radical attacks directly the copper, or that the radical abstracts from our metal salt directly the chlorine atom. And that is apparently so effective and runs probably maybe almost in a concerted way, that we are much broader in the type of alkenes we can use. So again, the take-home lesson maybe for all of us is that sometimes if we want to do a certain reaction where we want to add a radical across a double bond, we should think about different ways to make that. And I showed you this yesterday also with these nitroalkyl radicals. You could do it oxidative or reductively, and here you have a possibility to do this either by an electron transfer or by a hydrogen atom transfer process. And I would like to point out something else, which and I must say again, this is was very, very hard work from, you can see here probably from the name, is two of my Indian co-workers. Tirtha Mandal, he came with a European project as a postdoc, and then Mangesh Ghosh, who started his PhD in my group. And so they worked both really, really hard on this. Because in the beginning, we've been using a lot of these copper phenanthroline complexes, which I showed you, and they didn't work for this chemistry. And then they found out that these heteroleptic complexes, that they work very nicely. And they are also very easily formed, because when you mix a copper-1 salt, like copper chloride, when you mix this with a phenanthroline and the phosphine, 1-to-1, these heteroleptic complexes form very selectively, and you're not forming the homoleptic complexes. And so they found out about this, and initially we thought, okay, this is working because it has a very strong reduction power. So here it is minus 1.64. That was clear that this is enough for the copper for the acid chlorides. And then put the arrow on the wrong wrong one. And then they also, these complexes have very long excited state lifetimes. And so initially we thought that this long excited state lifetime is needed for this type of transformation. But on the other hand, we had done many other reactions, ATRA reactions, which does the copper phenanthroline type ligand. So why didn't it work here? And why are these heteroleptic complexes so good? Okay, good oxidation and reduction potential and also long excited state lifetimes. But we found out something else here, and that is, I think I should get a new page here. Oh, interesting. If I discard it, I erase it. Okay. And the one thing we notice, and this might be in general the interaction of these heteroleptic complexes, is if you have a heteroleptic complex which has two types of ligands on there, this is what you can easily prepare, and this is a copper 1 complex. But if you irradiate this in the presence of your acid chloride, copper 1 does really prefer to have phosphine ligands on there. And so what happens is, if you're irradiating this with in the presence of the acid chloride, it will form such a dimer. And then here you have presumably your cation still here. So if this is a copper 1 complex, we had like an anion here, BF4 minus. And so if we make the stoichiometric equation, then it would look like this. And you can see the interesting thing what happens. It's losing the nitrogen ligand. It's not losing the phosphine ligand. And that was something for us which was not obvious at that point. We looked in the literature, and there was a paper from Greg Fu, which we talked yesterday about these nucleophilic substitutions. And he, in one of his nucleophilic substitutions, noticed the same thing. And he pointed that also out, that the copper 1 coordinates with the phosphine. But then once you do the electron transfer, so once this goes then to, you reduce formally your acyl chloride, and so you might now make the acyl radical, and you go to copper 2. And what happens is it exchanges the ligand again. The copper 2 coordinates the nitrogen ligand. Copper 2 doesn't like phosphine. Copper 2 likes nitrogen. Copper 2 is more electrophilic, phosphine soft, copper 2 hard. If you look in the literature, that's then what we did. We checked, are there any copper 2 phosphine complexes known? And there are some papers which describe it from the 70s and 80s. And so I asked my coworker, and I say, can we prepare one so that we have a comparison and can do it? And they said it's not working. We cannot do it. We can do copper 1 phosphines. We cannot do copper 2 phosphines. So probably these literature reports are not correct. And this is an interesting interaction, how the mode of action might be. So it's not the heteroleptic complex which is doing the chemistry, but it's the copper 1, as long as it's copper 1, it's the copper phosphine complex. If it's copper 2, it's the copper nitrogen complex, which then also stabilizes and then indeed might give us the chemistry which we always would propose, is that these copper 2 phenanthroline complexes can interact very well with radicals. And so we thought that this is an interesting, really interesting finding, and this is probably the success that this reaction works so well. So you have it then again in the handouts, you have it here again, right? So you start with the heteroleptic complex because this is easily prepared, but then once you have in the presence of a chloride source, like your acid chloride, copper 1 phosphine complex, which forms is on copper 1, and then after the electron transfer, the phosphine ligand exchanges for the nitrogen ligand. And we could show this by NMR, we could show this by EPR in quite a number of ways. And here you see, and I really very much appreciate this from Mangesh and Tirtha. You see, they have an amazing number of examples and very meaningful examples. Let me point this also out. Oh, okay, I don't have it on. Don't have it on this slide. But what they did is, and that's also something very often that you find in papers, when you read papers and they say, we have 50 examples. The question is, how meaningful are the examples, right? Sometimes you have an aromatic ring, and then you put para-methyl, para-t-butyl, para-ethyl, and so on. These are not really meaningful examples. And so currently also the journals, many journals say, don't give us 50 examples, give us 10 examples, but the 10 examples should be meaningful. So you should have activated alkenes like vinyl arenes. Beside the phenyl, maybe heteroatom, some functional groups in there, electron-rich, electron-poor, have unactivated alkenes, have different substituents, so have terminal alkenes, 1,1 substituted, 1,2, 1,3, and so again, we tried all this, and the only alkenes this protocol doesn't work are tetra-substituted alkenes. It's probably understandable because they become sterically very hindered, but even tri-substituted alkenes still work. Show that it is compatible with functional groups. And so Mangesh and Tirtha showed that you can have epoxides in your alkenes. You can have boranes in the alkenes, halides, alcohols, amines. So they showed a very, very broad scope. And so indeed, in the end, there 100 examples came out. And then the other thing I liked very much is they are both very, very ambitious. And so they had already a good number of examples. And I said to them, I think this is a great paper, we should publish this. And what do you think? We submit this to Anjuman, to our JACs, because I thought that's pretty cool. And they said, no. We need a better journey. So I would not have dared this. And they said, no, tell us what to do. We need to submit this to, and then they settled on Nature Catalysis. And I thought, I told them, this is a long shot. And again, it is a very, very long shot because we submitted this paper in September. And then it took like 4 weeks until the editor decided that it goes out for review. Then after 6 weeks, the first review reports came back. They were all positive, 3 review reports. But then they raised questions, especially to the mechanism. And again, Tirtha and Mangesh wanted to go back over Christmas to India. And he said, I'm not leaving. I need to do revisions now. And I convinced him, I said, we are able to do this until Christmas. So then you should still leave. And they were working day and night in the lab. And on Christmas Day, 24th of December, I filed the revisions. And 2 months later, the review reports came back, and they had sent it to a fourth reviewer because we had a new X-ray structure in there. And they said, now we need to ask an expert in X-ray crystallography if your structure is good. And then this reviewer came back and the first 3 reviewers said it's great, it can be published, but the fourth reviewer had, again, a few questions, and he had new questions, right? And so again, Tirtha and Mangesh said, okay, we close our eyes, we do everything this reviewer wants to do, and again, push this through. And the paper got accepted yesterday. So it was 6 months, essentially, what it did. And sometimes you have to try. Sometimes it will not work, absolutely. You have to balance this. We had the feeling that with 100 examples, with really intensive, extensive mechanistic studies, we have a chance. And still, even up in the very end, I was not sure it would work. But if you don't try, it will not work. And that's what I think told you earlier. I review a lot of PhD theses from India, and there is very, very, very good chemistry in there. And it is very often undersold. You publish it in good journals, but not in top journals. And you, together with your supervisors, you should always ask yourself, what can we try? And of course, also, we don't do this. We don't submit papers to high-impact journals where I know we don't have a chance. but we very often try to see what can we do in order to bring it there, to have a chance. And then with journals like Angewandte or JAX, it works maybe in 3 cases out of 10. It's still, rejection rates are high. But I believe you should try, and as I say, a lot of the chemistry I see coming from Indian labs are really good about this. And so here, this would be essentially our conclusion, right? We have 2 different protocols where we make acyl radicals, but with the one protocol where we do the homolysis starting from iron 3, we can also do it from iron copper 2, but copper 2 is not as effective. We can engage the acyl radicals, but we can only do it with electron withdrawing alkenes. And then the other protocol from the acid chlorides, where we have the copper 2 then to assist the process in radical stabilization, this allows us essentially to go through the whole range of alkenes. Okay, so this was the one thing I wanted to say. We have coffee tea break at 11? At 11, okay, so then I think this was the last, last slide I had here. Okay, then I just give as a teaser, because we have 5 more minutes, I give you as a teaser the next chapter I want to discuss with you. And the next chapter I want to discuss with you is energy transfer. We did so far electron transfer in all these cases. So now we do energy transfer, and okay, it's working again. So the tea is not here, so we continue a moment. So in the second part, I would like to introduce energy transfer to you, and that is complementary as the other activation mode to electron transfer. With the electron transfer, the photocatalyst will transfer an electron or take an electron from the substrate. In the energy transfer, the catalyst might transfer energy. And one, I think, very exciting application for this is what I think originally the term was coined by Jimmy Weaver. I think that's at least where I read it the first time in the paper, uphill catalysis. And the idea of this, let me just show you a diagram first before we go into this. The idea is that if you have a starting material, and if you want to go from the starting material to the product, the reaction usually works if it is exergonic, right? So the starting material is here somewhere, and then you go to a product which is lower in energy. And so, of course, there's an activation barrier, but thermodynamically, this is favored. And if you want to run an unfavored reaction thermodynamically, then typically what you need to do is you need to use high energy reagent. And one of the examples for this, which we looked in earlier, is that if you do the cyclopropionation of a furane, this would be energetically uphill if that would, if you would just look at this alone. You break the aromaticity, you make a strained ring, and so on and so on. But you counter this by having a high energy reagent, like a diazo compound, right? And so this way you essentially lift your starting materials because you have a high energy reagent, and if this extrudes nitrogen and makes the carbene, you have generated a highly reactive intermediate on a high energy level, right? And so this is what we very often do in many type of reactions. Very often we use strong bases like butyl lithium, LDA, and so on. It's always the same thing. We're making a reactive intermediate which is high in energy, and we are able to do this by specialized stoichiometric reagents. But the idea with photochemistry can be different, because with photochemistry, you might be able to simply lift your starting material to a excited state, and the excited state is much higher in energy than the ground state. And then from there, if you go to a product, everything might be thermodynamically downhill. And we might have had this also in these SET, in these photoredox reactions which we had, but we talked a lot about these ATRA reactions, right, where we have an alkene and then add a radical precursor, and we are getting something like this, right? This is probably not uphill, this is downhill. If you again if you just try to make a guess, you would say, hey, wait a minute, I'm exchanging pi bonds for sigma bonds, right? And that must be thermodynamically downhill. So all the examples I have shown you in the previous section, where of course would go through an excited state, but nevertheless, if you look at the reaction coordinate, it would still look somehow like this, where the product is lower in energy than the starting materials. But I would like, with this energy transfer, there are now a lot of examples known where you actually start from starting materials, and these starting materials are lower in energy than the product. So the reaction is endergonic, and the way you do this is that you bring in the energy in form from light, you bring in the energy, and this way you can go to a thermodynamically higher lying products. And I think that is exciting for many applications. So first of all, it's exciting for reactions you want to drive, which might be thermodynamically unfavored. But also, and I will show you some shy examples of this, it might have relevance to store sunlight in form of chemical energy, right? Because if you have a process which is thermodynamically uphill, you have essentially stored the energy you get from your light source, and ideally it would be sunlight, and you would have converted it into chemical bonds. And then if you in some reason should be able to release it again, you might have a chemical storage system. As I say, one has to be very careful, very shy, and especially things where you convert a product, a starting material, to a higher energy product. There's still many different difficulties and obstacles to use this as an energy storage form. But it's one approach you can think about. And I think the interesting or the important thing is we're pretty good already in producing renewable energy, but we are terrible in storing it. And storage is a huge problem in all kinds of ways. We do lithium batteries, and you see how well this works. We are changing every 30 minutes. That's not lithium probably, that's nickel hydride or so. We're changing the batteries a lot. But also just to store 1 kilowatt hour, I think 0.7 kilowatt hours, you need 1 kilogram of lithium, right? So really energy storage, and have it in a way that you can transport it from A to B is a big issue. And that might, if we think about storing energy in form from of chemicals, chemical bonds, this might be one way to think about this. And so therefore, these energy transfer can be quite useful. So you guys stop me when the tea has arrived, right? So it's not my fault. They told me I continue until the tea arrives. Okay. So if we think about energy transfer, we bring a molecule into its excited state. But in this case, other than in the photoredox chemistry, we don't transfer an electron. We have a catalyst which is in the excited state, and then might transfer the energy to a substrate. And this can also work directly on the substrate, and I think one of the best examples for this are carbonyl compounds, right? If you shine light on a carbonyl compound with the right wavelengths, then you are able to bring this in the excited state, and then the same thing like which we discussed earlier, you bring it into the first excited singlet state, and then it has to do an intersystem crossing, and then from the triplet state, you can get reactions out of this. And this triplet energy, the energy where the triplet is higher than the ground state, this is the energy you can transfer to a substrate, right? So very important, you need to know how big the gap is, the energy gap, the triplet gap is, and you need to match it with your substrate so that this reaction can work. And out from the 60s and 70s, there are quite a number of reactions known which can utilize the idea that you can use carbonyl groups, excite them, bring them into the excited state, and then do different type of reactions. And I'm going to show these to you a little bit. I'm not sure if you know them already. Also, the Norrish 1 and Norrish 2 type reactions are typical cases for carbonyl groups, but then also very important is the Paterno-Büchi reaction. It's a 2+2 cycloaddition with alkenes, which can do this, and then you can also do isomerizations and photoreductions. And so again, here's another representation of this energy diagram which I showed you earlier. So we use excited states to lift up our starting materials, and then this can go both ways. It can either go to a thermodynamically less favored product, but it can also help you to start from the excited state and then overcome a very high transition state barrier, right? And the advantage is if you start from the excited state, from the activated starting materials, this might be easier than if you would start from the ground state. Okay, so the Norrish type 1 cleavage is a reaction which is, depends in many cases quite useful, especially when you can do this intramolecular. And so what this is doing, let me get the, oops. Okay, so doesn't matter. We have it here already. Nope. This one here, right? So what the Norrish 1 cleavages do, if you excite a carbonyl group, then the adjacent carbon-carbon bond might cleave. And what you are generating is radicals, and this might occur twice. Driving force, one of the driving forces probably that you make a relatively stable carbon monoxide here. And then the two radicals might recombine. Something we don't see so often. We talk about transient radicals usually do not find themselves. But then if this can be done in an intramolecular scenario, this might be a very useful and good reaction. And you see an example here where you have this cyclopentanone here, and then under the irradiation you go to a cyclobutanone and carbon monoxide, right? This is exactly the reaction we have seen up here. And again, in the terms, if you think about uphill chemistry, one would have to look at carefully also at the carbonyl group, but you see you make a more strained system. So you probably introduce the chemical, the light energy which you have been using here, you introduce in the end in your product. This could not be really used for an energy storage system because this is not reversible any longer, right? Because the carbon monoxide is gone. But it shows you that you can make strain systems in order to do this. And then the NORIS2 type cleavage can occur if your carbonyl group has in the 1,5 position, so if I calculate my carbonyl oxygen as 1, 2, 3, 4, 5, if I have a hydrogen, then this hydrogen can get abstracted from the excited state of the carbonyl group. The best way to think about these excited states is always as a diradical. So if you go if you do the excitation, if you want to think about the chemistry which kind of out of this, draw it as a diradical, and then you can get chemistry out of this. And so typically what is a very good process are these 1,5 hydrogen shifts, and you can easily see why that is, right? Because it goes, if this gets transferred here to the excited state of the oxygen, it goes through a 6-member transition state, and that is very, very useful, and that typically is favored over a 5-member transition state or even larger rings, right? So these 1,5 shifts are very, very typical, and then you see that you're generating, and it's already seen here, my radical dots have been a little bit big. You can see that you're forming a new diradical, right? You have transferred the hydrogen to the oxygen, and then you have the radical center on this carbon, and you have the radical center on this carbon. And this can do now two things. It can do a radical coupling, and then again you form cyclobutanones. So again, that's probably definitely thermodynamically, if you think about this again, it's definitely thermodynamically uphill, because you're sacrificing your very stable carbon-oxygen double bond. We talked about this. And at the same time, you make a cyclobutane ring. Cyclopropane, we talked about the ring strain. I said it's about 27 kcal per mole. Cyclobutane is about the same. It's also in this range. So it's quite a strange system. And so therefore, one of the alternatives is instead of doing the cyclization, it can also undergo cleavage. If it cleaves between this carbon-carbon bond, then it would form two alkenes in this moment, and that is also a reaction pathway, which typically you have a competition between these two reaction pathways, and then your enol ultimately tautomerizes over to the acyl compound. And so these are NORIS1 and NORIS2, and I just said that the 1,5 shift is usually the one which is preferred, but if you have a situation where the 1,5 shift might come from a sterically hindered position, then also the 1,6 shift might be feasible, and this is a very interesting example shown from Axel Griesbeck, who is a very famous, well-known photochemist in Germany, and he has been able to show this example, where instead of the 1,5 shift, the 1,6 shift, which would go now through a 7-member transition state, occurs. Again, he's making this diradical, and now there's another, that's the interesting thing. So how is this stabilizing themselves? Here we saw what it can do. It can cleave by fragmentation this bond and form these two alkenes, or it can do the radical radical coupling. So how would it have been here? It could have probably also done the radical radical coupling to see a 5-membered ring here. I'm not sure why this didn't happen, if that was a problem for steric reasons. And instead, it would do now a 1,4 hydrogen shift. So it would shift this hydrogen to this radical center here. And then you can see that this way you're generating a new double bond here in order to do this. So this is something you always have at least to consider. The 1,5 hydrogen shift is the most favorable one because it goes through 6-membered ring. But if it for some reason cannot do, you can observe 1,6, you can observe 1,4. And again, this is a contrast thermodynamic process. We are sacrificing a very stable carbonyl CO double bond. And what we are getting out in the end is we are getting out a CC double bond, right? So that again has probably gone 20 kcal downhill. Should I still no T? Yeah, it's not my fault. I should have a big sign here. It's not my fault. Okay, we already talked. I had a question for this, but we already have answered this, that it is. Now tea? Okay, guys, tea break. I see some of you need it. I understand this. So let's have a small tea break.